Hello and welcome to this session. Here we're going to dive deeper into the usage of VopSops. We're going to see certain functions, and what we especially are going to focus on is on how we can work and do operations on vectors so that you can create all kinds of constructions to help you out to generate the tools that you need. Now, as an example, we have over here a algorithm that calculates the proper lengths for the normals, so that if we are going to move along the normals, that they have like the proper lengths, so that all the lines will stay parallel to each other. So if we look at the previous one, the ghost one, as you can see, we're just keeping everything parallel to that. So this can be useful for all kinds of things, for example generating walls or creating some other tools such as straight skeleton. It's just a preparation for that. If you don't know what a straight skeleton is, just look it up and you will find some good examples of what it is. It's very useful if you want to generate procedurally roofs and other kinds of things. The tools we're especially going to see are the dot product, the cross products. I know it's math again, but hopefully when you can play with it in a visual way, it will help you out quite a bit easier. And we're going to work also with modulo. Modulo is also a very powerful mathematical function which lets you do all kinds of things. Okay. So let's start from scratch so that we have a good beginning. So the first thing that you will need is some kind of a curve, just a simple shape. It doesn't matter what kind of curve. For now, we're gonna keep it simple, so make sure the curve is generated just on a flat plane. So next thing you're gonna do is you're gonna generate a VopSop, connect it to the first input so that we are going to do operations on all of the points within the first operation. So first step that we're going to do is the following. We need to find the tangents on this curve. That's the first step that we need to do in order to build everything from that. And the tangents are the lines which are just straight on the corner. Perhaps a better way to look at it, tangent, and let's see if I can find a good image of a tangent. Well, yeah, here we can find tangents. So these are lines which are just perpendicular or parallel to the surface of the circle. So these are all tangent lines. So this line, the tangent line, are the ones that we need to construct. Now, how are we going to construct that? Well, we're going to do first a few things. First of all, we're going to try and figure out the direction of the incoming line, which will be a vector aiming this direction, and we're going to find the direction of the outgoing line, which would be then a direction just following what we see over here. So these are the first two steps. So how do we control this? And perhaps I'm going to create for that just another thing. Add, and I'm gonna add like 2 points. 1 point in the center, and then another point which we can translate to another spot. So I'm just going to add over here transform, so I can move this point around. You can see it on the number over here, and then we're gonna merge them back together so that we have like point 0 which is in the center first, and then point 1 which is the point that we're going to move around. So we have 2 points over here. So imagine we just have like these 2 points. They're not connected, they don't have any kind of shape. Now what we're going to do is we're gonna make sure that we find the vector which is aiming towards this point. Now how do you do that? In fact, this is not so difficult. So you can see over here we have the x and the z direction. So if you want to get over here a vector aiming directly to this point, the only thing you need to do is to take this point's position and subtract it from this point. Now, because this point is sitting on a 0 location, this might not be too difficult to imagine what it's going to be like. So I think we have over here a position of, let's say, 1, 2, 3, 4, 5. So that's 2.5, and then 1, 2, 3, 4, 5, 6. So this is 3. So we have a value of 3 in the x direction, and we have a value of 2.5 in the z direction. So if you're gonna subtract this position from a point which is on 0, we're gonna get exactly the opposite. And we're gonna get like a -3 and a -2.5. Now if you would have a vector which is exactly a -3 and a -2.5, you have indeed a vector aiming directly towards point 0. So that's what we're going to do. So let's see whether we can create this vector. Now, one thing, just to make sure that we can see what's going on, I'm going to switch this off because I had that generated before. So if you want to have always a visible result of what you're doing inside of VexVectors, make sure that you pin down this viewport. Then it's going to be locked on this node, this position. It's also going to evaluate always on this level. Another thing that you will need is to make sure that you make the normals visible so that we can see what's going on. So if we go inside by pressing I, we see over here the point position. So what we want to get is, we want to get like the point position of this point and the point position of the next point. So for that, we're going to go to geometry and we're going to import an attribute. And the attribute that we're going to import is, it is going to be a vector attribute because it's position, so because we want to subtract two positions, and the attribute name is going to be P. Now the operation input index, we're going to remain the same. We don't want to have like the input from something else. We're going to take input 0, so that's something which will remain the same. But we have over here an input which is not listed right here, which is the point number. And so basically what we're going to do right now is we're gonna take the point number, the current point number, and we're gonna add a value to that. So if you're gonna add constant, then we're going to add just 1 to each number over here. And so now we're getting for point 0, we get over here point 1's position. So let me just add over here a subtraction. That's what we're going to do. We're going to subtract point position from the first point, 0, and from that we're going to subtract this point over here. And this result we're going to just feed into the point normal. Okay, so this is what we're getting for point 0, which is normal. Point 1 obviously gets something totally different, and the reason basically is that over here we're just adding a constant number. Now the point number when it is on point 1 is going to be added with 1, and so we try to get like the attribute of point 2, which doesn't exist. So by default it's going to take like a 0 value. So it's going to be a 0 vector, vector 0, 0, 0. Now if we're going to subtract 0 from this position, we get indeed this vector. So this is perfectly alright. Now let us connect this now with the curve and see what we're getting. So as you can see, we get all our vectors. We get like point 1 being subtracted from point 0, and so we get its vector this way. Now I'm going to add an add node, which is going to remove, or which we're going to use to remove all the geometry but keep the point, so that we can clearly see what's going on with these normals. Now the direction of the normals is not what it's not the direction we want to have. We want to have, like I said before, we want to have like the direction of this line, and we want to have the direction for this line for point 1. So point 1 is going to have like both this direction and this direction. So let's first start with the direction we have over here. So let's get it into the proper direction, and the way how we can do is by simply just inverting the subtraction. We're not going to subtract the position of the next point with the current point. What we're going to do is we're going to subtract the current point from the next point. So it's just by pressing R, and you can reverse the connections over here. Now suddenly you will see all those normals have disappeared, but we can see them over here when we have removed all the geometry. So these are all our normals that we have. Okay, now as you can see, we have the last normal pointing directly at 0 because of exactly the reason that I told right over here. Now we're gonna keep that. We're going to forget about these 2 points, the end point and the start point. That's something we're gonna solve later. Right now we're just going to focus on everything within. Now the other function that we're gonna use is a normalize, because as you can see right now, all these lines, they have like exactly the length of the differences in point positions. So when we normalize them, we're going to give them like a length value of 1. And so now we have like the proper aiming direction and also with a decent length. Okay, so now we have to do exactly the same thing but for the next one. So let's get up again, let's see. So we need to get like this direction over here, a decent vector right here. So how can we calculate that one? Well, it's going to be simple in that sense that first we added a value. What we now want to do is we want to subtract a number value. So if we're on point 1, we also need to get the position of point 0. So we're just going to copy the whole thing over here, and also perhaps with subtract as well and normalize, just copy the whole thing. And we're gonna paste it right underneath. So we have 2 subtractions right now. And the only thing that we're going to change is over here, instead of adding 1, we're going to make it like adding a minus 1. And let's see when we connect it what we're getting. So right now I don't see anything, and this makes me think that probably this vector is aiming towards the point 0. Let's have a look, let's see what's happening. And indeed that's the thing what's happening. Which is of course logical, since we've taken this point and we subtract the current point from that. So again, you have to change the connection. And so now we can see we have both of them right over here. So if we connect this one and this one, we can switch. Perhaps it's better to show it over here. This one, this one, this one. So how do we get like an average of both of those? Well, it's actually fairly simple. We just have to add both of the vectors together. So if we add them together, normalized vector 1 and normalized vector 2, then they're going to show just up right exactly in the middle. Let's create some extra helpers for that, because it's useful that we can see the normals, but it would be even more useful if you could see like other vectors as well. So what we can do over here is we can add an attribute. And let's use some attributes that you can use for other things as well. So over here at geometry, create or add attribute over here, and the attribute we're going to add is like, first is going to be an up attribute, and let's say that we connect this one over here to the up attribute, just give it the name up. And what you can do as well is in this node, it's very handy, you have attribute, but you can also create like a local variable name, which is up, like this. Okay, so copy this again, and this one we're going to make like an at attribute, like looking at something, just like an arbitrary choice, because the proper name could be a bitangent or something like that. So let's connect them over here. So what we've done right now is, apart from calculating the average over here, which I'm going to make more clear or more visible with showing the other things, we've now added like two extra attributes. We have now a normal, we have the point position of course, and we have now added like an extra attribute, an up and an add. And something you can see over here, if you go to the details view, and we go up, see with the selected node, we have like an up attribute, and we have now an add attribute as well, two vectors. Now let's make sure that we can see those, and that's something we can do using what we see over here, the custom operations. Now we don't see anything appearing over here, so we have to first create our custom visualizers for this. So by pressing D over the viewport, you see right here that we have something to show as custom. So the thing that we're going to create is right here, an attribute vector, a vector1, and let's create two immediately. We can make them visible or not. So first what we're going to do is we're going to edit them, and we're going to give them a name. The name is going to be up, and the attribute we're going to use is up as well. Class is a point attribute. The scale can be 1. I don't have any problem with that, and we can give it like our own color, which is going to be green, and the selected green color is going to be something like this, 0.510, something like this. Perhaps make it even more yellowish. Yeah. So now we have like just the color, and we have the selected color. For the up value accept, and let's do that for this one as well. Let's edit this one, add attribute add, and this one we're gonna give also a color override. It's going to be reddish, and let's make it a little bit orangey, something like this. Apply. Good. So if you want to visualize now both of those attributes, what you can do is over here, just you can see them appearing in the list, and you can just add right here their values. And so as you can see, our two vectors that we have gotten, like from the incoming line and from the outgoing line, if you add them together, you nicely get like this averaged direction, which makes perfectly sense. So if we go inside, the thing that we're going to do right now is we're going to normalize it, because a vector is like, if you average them, you can see that this line is just sitting right in the middle, but is sometimes longer and shorter, and that's because it's going to add up both of the dot lengths that you see over here, but that's something we're going to see later. So normalizing it gives you like the proper direction and a proper length. So if we see this now combined with our curves, you can see that we have generated our tangents, which is great. Okay, now we need to do the following trick. We need to find something else. What we need to get right now is the vectors which are perpendicular on the tangents. So they're going to sit like perpendicular on the tangent, so that they are crossing right through the middle of the corner that we have over here. And so if you have like a corner, it should go right through the middle of that corner, dividing both parts in equal halves. So how are we going to do that? Well, for that we're going to use a cross product. Now it's not so or not that important that you know exactly what a cross product is doing. It's not that difficult to see what's doing, but it's more important that you know what you can do with it. And the thing that you can use a cross product for is actually to reconstruct all kinds of axes. If you know that an axis, a matrix, is consisting out of like multiple vectors, then you can see how you can reconstruct those things, and you can use a cross product, for example, to create your own aim constraint or things like that. So a cross product, essentially what it is doing, it's taking in two vectors and it's using those two vectors to generate like a new vector, which is going to sit perpendicular on the surface these two vectors are creating. So you could see this as a description of a surface. So if you have like two lines, if you would make them like endlessly long, and you would copy this one over an endless long red one, and you would copy the red one over an endlessly long blue one, you can see you can get some kind of a grid, a little bit a distorted grid over here, but it would exactly describe a surface. So with the cross product, you're going to create like a vector which is like sitting perpendicular onto that. So if all is going well, what we're going to see is we're going to see like vectors sitting straight up into the y direction or in a negative y direction, because we've created our curve over here. So let's go in, and since we have like added proper names, we can know what we can find what we need. So we have over here the add, and we have over here the normal. So let's see, and let's go in. So the thing that we're going to use is the following. It doesn't matter actually, we can use both up and add to create like the normal, but I'm gonna do it now with this version, with what we have over here. So we're gonna take not the up but the add, and we're gonna make like a cross product from that. Cross product, and we're gonna cross product this one together with this one. So let's see what we're gonna get. Let's connect it to the add again, and now as you can see, we have like all these vectors pointing upwards or vectors pointing downwards. Now as you can see, we have longer and shorter vectors. This one is a fairly short one, this is even shorter, and then we have pretty long ones. Now the thing is, the length of this is also an indication, or is a reflection on how much they differ in angle. So if we're going to go up and we're gonna play with our point positions over here, you're gonna see that the closer I bring it to a straight line, the shorter this line is going to get. And once you get like completely straight, completely to a straight line, it's going to be falling to a zero. So when I just would move it like a little bit further, it would fall to zero, and then it would go up again into the other direction depending on the difference. So this is what dot product is doing. So keep that in mind. You can use it for all kinds of things. I used it to generate, for example, a rocket guidance system in the game once, and which is pretty fun to use. So the next step would be, and that's something you can try to figure out, the following. So in order to get now the perpendicular on this tangent over here, you can use a few things that we've generated right here. So you can see them, and you have to figure out which one, and you would have to do like the same thing over again what we just did in order to get like this perpendicular arrow. Now you're gonna see the result that you're gonna get is going to be like elements which are in this direction, vectors which are in this direction for the convex corners, and then we're gonna get like inverted for the concave corners. So that's normal, they're not all going to point outwards. That's something we will have to fix later. Okay, so you can do that yourself, then pause the video and otherwise I will show you and continue how the rest is looking like. Alright, so what you need to do is the following. First we have created this cross product. Make sure that we make it all unit length. So again, we're going to use a normalize. So we get them to all equal lengths. Now over here we have like nice perpendicular lines. We have both over here our tangent curve, and we have now this up and down looking curve. So the next step what we need in order to get our perpendicular one, and that's something I'm going to connect over here with the new up, is the following. We need to do again a new cross product. And as you can see, there's inverted over here. This one is going right up. So let's see if I can reverse that like this. So now we have like our normals aiming outward. Well, I'm just going to keep that as it was for the normal at least, and I'm going to connect this one to the up, so we get now all our axes. And as you can see clearly is that we've constructed ourselves a system which is generating like a proper axis. Well, in order to make like really properly connected, what you can do is we can make the up over here, the add is going to be this one, and the end result is going to be normal. So this looks more like a normal axis, x, y, z. So as you can see, you can create your own axis that way. Good, so we now do have this step, but as you can see, we have like these elements pointing inwards, and that's something I don't want to have. We want to make sure that only these elements are going to point outwards. Now, how are we going to solve that? Well, it's again not that difficult. Look at the up vector, which is the green one. Now, what I want to have is each time that it is aiming downwards, I want to invert it. So the thing that we're going to do is the following. First of all, we're going to make this value absolute. And absolute means that you're just removing the minus sign in front of every number. So if you had like a -1, that becomes 1. If you would have a -20, that would become just 20. This is how it is working. So now that we have inverted this, what we can do, we can feed it back into the cross product, and now you will see the cross product is going to calculate it again, and so now all our normals are aiming into the proper direction. Good, so that brings us right over here now. Let's go a bit further. Let's see what else we can do. Now the next step, it's a little bit more difficult to do. Is the following: is now we need to get the proper lengths over here for our normals, and the proper length is actually the length it needs to have in order to have like a unified perpendicular line on it on this curvage. So it needs to be as long as 1 when being perpendicular over here. So how can we find this number? That's where the dot product will come in, and that makes it interesting. Now a dot product, again, you don't need to know exactly what it does or how it works. You need to know what it does, but you don't need to know exactly how it works. What it does for you is you could see it as make a projection of one vector onto another. So if we would see, let's say that we take this one right over here, and let's go back up to this version. So a dot product would actually project this red one onto the blue one, for example. And what you would get is the value of that length projected on this curve. So as you can see, this is a normalized vector, and if you would project it like perpendicular onto this projector, you would see you get a value of, let's say, 0.85 or something like that. Now this is a very interesting value because that's exact the value that we need complemented to multiply right over here. Let me show you. So let's create a dot product. And let's create our dot product from the, where is it? This one, and the cross product that we have over here. This is going to be our dot product. The other thing which is important is that it's going to be an absolute value at all times. So the dot product that we're going to get is going to be absolute. Because over here, if we would project this one on this curve, get like a negative value. We need like a positive to multiply. Now, if you would just do a multiplication, that wouldn't work. The thing what we need is that if it is, let's say, a value of 0, then nothing should change. If it becomes like a very small value, like over here, then it should change quite a bit. So a complement would ensure this to happen. A complement would make sure that everything would be inverted. For example, if we have like a projection of a line over here, then its value would be, its dot product would be 0, and a complement is 1 minus 0, so it becomes 1, and so therefore if we divide 1 by 1, it's going to stay 1. If we would have like a little bit of an angle over here, let's move again to this one over here, which is a pretty sharp one. If we have like a dot product of 8.5 and we take a complement of that, 8.5, you would get like 0.15 instead of 8.5. The complement is just like 1 minus the 8.5 you would get over here, so you get 0.15. If you divide this length by 0.15, you get something like a 6 or a 7. And this is going to greatly enhance the length of this normal. So that's what we need, a complement. And as you can see, you see it also over here, complement is just 1 minus an incoming value. So we can take this one over here. And now what we're going to do is we're going to divide the cross product over here by this complement. Divide by this input. And as you can see, we have like all these very long values, which is not exactly what I had in mind. Because as you can see, they're way too long. And for one reason or another, I can't grasp exactly what's going wrong over here. What I do know is we have this cross product over here, which seems to be a decent length for me, but I think it has something to do with the offset value that we get over here. So what we're going to do is the following. gonna take this value, which is just the tangent curve itself, as you can see, and we're gonna take the tangent curve in combination with what we have over here. So we're gonna dot the tangent curve right here. This is still not going to give us a perfect result, but at least I don't think we need to do a complement. Now we do have like the proper value. So as we can see, both of these values, we have the add value and we have over here, let's take this one again, point normal. So what we did right now is we created a cross product between this one and the red one, the blue one and the red one. Now since they're always in the same direction, we're getting like a decent dot product, and a dot product we don't have to invert or something or create a complement of. We can even remove the absolute value because this is not going to add anything new to that. So this is that result. So if we're going to look over here and we're going to move with a peak node, a peak allows you to move along the normals. You can see that we are moving for now in a proper direction. At least that is for all the points between the start and the end points. So now how are we going to solve this? Well, we need to solve the following. We need to make sure that if we're gonna get information of point 0 and we want to, or let's say we have point 1 and we want to subtract point 1 with point 0, then what you want to do is with point 0 you want to subtract point 7 over here. Now this is something we didn't do right here, so we need to build that first. And how can we build this? We need to make sure that everything goes around in some kind of a loop. So we need to make sure that the point number is going to go up from 0 to 7, and if we add 1 to it, it goes back to 0. So the first thing that you can use for that is a modulo. And modulo, what it basically does, it's giving you the rest value after a division. So pay attention. If you have, let's say, 10 modulo 4, then the rest value is going to be 2. If you have 9 modulo 4, then the rest value is going to be 1. Now what's going to happen, or what is a modulo doing? Basically it's doing the following. It's trying to divide a value with another given value. So 9, it's going to divide it by 4, and it's going to try to divide it by 4 as many times it can. So first time it's possible because 4 fits well in 9. 2 times is also possible because 8 fits perfectly within 9 as well. But then it can't go further, so after 2 times it's locked. So if you have 8 and you still need to get 9, then you have 1 as a rest value, and that's that rest value that we're talking about in modulo. Now this is very useful if you want to have, for example, an animation of a clock or something like that. If you want to have like something pointing into a certain direction, etc., and then moving back from start again. So imagine if you would add a timeline to an input of a modulo, and then you can set with fractions of 10 or something like that. Then you would have like a timer which goes from 0 to 10, from 0 to 10, from 0 to 10, from 0 to 10 each time. So those are the results of that with modulo. So now how are we going to use this in this context? So right here we're adding a value. So we have to make sure that this value is going to go around again. So what we're going to do is, after this add constant, we're going to put our modulo over here. And what is the modulo value going to be? Well, that's exactly the number of points that we have, the total number of points. So once it reaches that number of points, it's going to get back to 0. So that's one part. Okay, it seems to work fine. We don't see any result because we also need to do it over here. Now here it's going to be a bit more difficult because modulo is not going to work with negative values, and what we're doing over here is we're going to subtract off something over here. Now how can we get it to work right here as well? Well, again, we're going to use modulo, that's for sure. Modulo, and the modulo that we're going to use is again the total number of points. So this is going to work, but as you can see, we can't see any change over here. Well, in order to make sure that if we subtract one, that it's still doing a proper job, it's going to be actually quite simple. The thing that we're going to do is, before we're going to add something, we're going to add to the number of points, again the total number of points. So just add with the point number, the total number of points again. So again, it's going to be nicely synchronized for the rest. So if we now add a constant or subtract a constant of 1, you can see we have the total number of points and we subtract 1 of it. So this is going to give us 7 again. So now everything works fine within this modulo function, and so we now have like something which moves along these angles all the way. And so this is like the very first setup in order to create, for example, this straight skeleton I was talking about. Now, straight skeleton, what it is in fact doing, it's going to rebuild every time a new curve from the moment on one of the edges collapses or one of the points are connecting or crashing into the other side. If you want to know more about it, then just look it up, straight skeleton. And so then you do the whole calculation again and you start insetting this way, etc. So it's very powerful for all kinds of things. Find some kind of an inner skeleton of a shape. Alright, so now we have this. Now we have this peak function right over here. Now let's say that we want to include it immediately right in here, this peak function. So let's go over here, so make sure that we don't have to use this anymore. So what we can do now is we can use this normal value in order to add to the original position. And we're going to multiply this value then with an external parameter. So multiply, or you can call it scale, this value with a parameter, promote parameter. So as you can see, it's going to generate for us a parameter right over here. You can right mouse click and expose input, so you can see what's going on over here, and you can give it a decent name. So let's call this scale, and the name is going to be scale as well over here. You can give it also right here the name, so you can see what node it is, so it appears right over here. What you can do, you have like a default float value, which we're going to set to 0. Float range is going to be from minus, let's say minus 10 to plus 10. So you have like all kinds of options to set a little bit the interface, what you want to have. And so this result we're going to add to the point position. So if we take our point position, connect it to the add, and this multiply, so this vector, we're adding it as well, so we're feeding it into the point position. Then we have suddenly over here a scale value, and as you can see, we can move it along the scale value. And so you can do all kinds of nice little things. You can start, for example, to add a sine wave onto this motion so that everything starts to move in bizarre ways or something like that. So this is all possibilities. Perhaps I can show you what you can do is, for example, that for each point, so we have this value, and we're gonna take like the point number as an offset for the sine value. So we're going to add in this multiply. So with the scale, hang on, to see whether I do it properly. With our scale, and the scale is multiplying this value what you have over here, and what we need as well for the scale is that we're going to multiply our scale with a sinus wave. That's what we need to do. So if we're going to multiply the scale, we can do it immediately right here. So we need a sinus wave. Oh, that's something you can find in 3 geometric functions. We can find right here the cosine or the sine. We're gonna take the sine, and the sine is going to be this offset that we're using. So the point number is going to be an offset. We can perhaps better change it into a float integer, because it's the point number to float. Change it to this. And what else are we going to add over here? Well, we can add, for example, an extra input value. So let's add something which is going to be another parameter. Expose inputs. Let's call this one offset. Offsets. Offsets. Like this. And now we have this sine wave, which then we're going to multiply right over here. So as you can see, because of the numbering, we see already some kind of a change. And like this we can create a nice locomotion. So for example, the offset is going to be like time value. So if you start to play, it moves around very quickly. Let's multiply it by 0.1, and now we get something like this, and get some kind of a wavy kind of animation of elements moving in and out. So as you can see, you can just start playing around with all these math functions as many times as you want. Now what I strongly recommend is, now you've seen this video, really try to read and understand the functions we were talking about, like the modulo, the dot product, and the cross product that you see with images, for example, on the internet, also what you can do with it, and try to rebuild this whole thing again without using the video, and so that you can prove to yourself that you really understand what's going on. This way is how you really learn. Okay, so this concludes it for this video.